So let me first explain to you what setup do I have in the lab first, okay? Now, I do have a couple of bare metal servers. Let me share my screen. So I have a Kubernetes cluster, okay? And I'll talk a little bit more about that. This is a bare metal cluster, okay? Now you could do this on any Kubernetes cluster with NVIDIA GPUs. In my specific case, what we managed to do is set up a EKS anywhere bare metal cluster with NVIDIA GPUs, okay? Some people ask me, why EKS anywhere? And those are some things that are out of scope in this session, at least. I prefer EKS anywhere. But you could do this on Rancher, you could do this on OpenShift, you could do this in the public cloud or wherever you have a Kubernetes cluster with access to NVIDIA GPU or any other GPU, let's say that, right? Now, what you are seeing here are the two worker nodes, okay? And you can see the iDRAC IPs. These two worker nodes, if I just want to kind of highlight that they are coupled with L40S NVIDIA GPUs. So you can see the presence of L40S in worker node 1. And on the worker node 2, again, similarly, I do have the NVIDIA L40S. Now, why L40S? Why not A100s or H100s? I just had this lab as a resource capability available to me. So I'm using L40S. We could have a better, let's say a paradigm that we can work with. But in this case, we'll work with NVIDIA L40S. So these are the two worker nodes. And then I'm on my terminal, which I generally use to access my cluster. The cluster itself takes roughly about 30 minutes to set up, not anything beyond that, okay? It's a very pretty simple way to actually get up and running with an EKS Anywhere cluster on bare metal. So if you look at my nodes, there are 3 nodes. The control plane, obviously, ideally, it should be a 5 node, but this is a 3 node minimal cluster with 1 control plane, 2 worker nodes. And like you saw that, this is the data plane IP is actually 198.67 and 198.68. The iDRAC is 197.67 and 197.68. Okay. I could run previously in the last week, I was running a Ubuntu image. This week, I'm running a Red Hat image. So both are possible. It doesn't matter actually whether you are working with a Red Hat image or you're working with a Ubuntu image. Again, this is the cluster that I have. Like I said, 2 control plane nodes, both equipped with NVIDIA L40S. Okay. So obviously, before we start a Kubernetes cluster, to deploy GPU applications on a Kubernetes cluster, you typically need to actually deploy the support for those GPU cards. And in the case of NVIDIA, there are many things that you have to actually individually deploy, like the device drivers, the plugins, and ABC, based on the compatibility of your cards and things like that. Or NVIDIA has come up with a magic wand. I'm pretty sure that most of you would know that, but just to kind of say that, it's a magic wand. If I say kubectl get pods minus n GPU operator, you can see that one line, essentially one single line. If you have your cluster up and running, you have the NVIDIA GPUs there. One line is all it takes, a Helm command, to install all of this, which mitigates the entire pain process of actually deploying, compatible drivers, compatible CUDA toolkit, everything that you see here, which are running as applications in the Kubernetes cluster. They actually work hand in glove to provide access to the underlying GPUs to the CUDA kernels. Okay. So there's a lot that we can go about talking about, the NVIDIA GPU operator itself. But again, that's not the scope of this discussion. But what I wanted to kind of highlight is the ease with which this gets deployed. You get the Kubernetes cluster up and running about 30 minutes, or some other cluster. Punch in one command to get your GPU operator up and running. That's about it. Once your GPU pods are up and running, you can then start deploying your GPU-based applications. Now, so essentially speaking, machine learning models, I just drew up these sketches last night to highlight. They are powerful and complex. Essentially, what are they? They are mathematical structures. Nothing, at the end of the line, these are complex mathematical structures encoded in some framework, right? And that framework or language of choice, in most cases, basically happens to be Python frameworks, okay? So in the world of Python frameworks, you have multiple different frameworks that you can use to actually build and train these machine learning models or AI models, or whatever we call them. TensorFlow is very popular, Torch, PyTorch, very popular, but others included, right? So these are all nothing, but think of it basically as a mathematical structure encoded into a Python framework. Now with its Python, obviously it's a bunch of Python, right? You're writing a code of Python and doing something with that code with an intent, basically, right? And then the real question is, how do we run this code? How do you typically run a Python code, right? It's like running a Python script. If you have a Python environment, now that Python environment could be on a bare metal server, or it could be a virtualized VM or an EC2 instance, or even a containerized platform like a Kubernetes giving you access to a Python environment into a Docker container or a container running on top of Kubernetes. So doesn't matter whether it's bare metal, whether it's virtualized, or whether it's containerized. As long as the underlying infrastructure gives you the access to the Python libraries, you can run your code of Python. And what is that code of Python that we are talking about? It's a bunch of mathematical structures, highly sophisticated, encoded into a certain framework, okay? Now, these frameworks have been developed, matured over a period of time. Now, the next question is, you can run these mathematical equations on CPU or GPU, doesn't matter, okay? The only thing that matters is GPU is obviously better because of a number of reasons, and we will not delve into that, but when you want to perform these parallel operations in terms of mathematical computations, GPUs are the way to go. That gives you speed and agility and a lot more efficiency, right? So bare metal, virtualized or containerized, CPU or GPU. And then, I tend to kind of highlight this, but while the code can be run as a regular Python script, almost all of the times, most AI ML developers, they will typically use Jupyter notebooks, right? And I'll make this story very short, the narrative, but Jupyter notebooks are basically a web-based interactive, let's say, way to run your Python code onto a underlying compatible substrate, right? Now, what does a Jupyter notebook look like? It's, again, it's a bunch of Python code and you can run it basically, and it will execute that into the kernel actually, right? And interactively, it will basically, output and spit out the outcomes of every step of your code. Now, you could again run Jupyter notebooks on your personal laptop equally well, or on a server, or on a VM, or in Kubernetes. As a scaling effort, when people deploy Jupyter notebooks, they are typically done by a very popular framework or let's say ecosystem called as kubeflow. Kubeflow gives you access to build these notebooks or run these notebooks, and amongst many other things, this is one of the features of kubeflow. So obviously, when you have a Kubernetes cluster, which in this case, you have seen that we have, you can deploy kubeflow on top of this, which I have already deployed. Okay. So kubectl get namespaces So you can see that there is a namespace called as kubeflow. And inside of that, all the kubeflow components are running, which gives me access to deploying, anything that can be run with the support of kubeflow. kubeflow supports many different frameworks: PyTorch, TensorFlow, Hugging Face compatible models, Jupyter, everything else. So this is particularly installed in our cluster. GPU operator is installed. Now comes the point that what do we do with this basically, right? Once you get the kubeflow up and running, you basically end up in creating a new notebook, and that notebook can be used with CPU and in combination with GPUs. So this is how you create a notebook, and you have support for both CPU and GPU. If you have GPUs in your cluster, Kubernetes cluster, you can run the support of GPU in your kubeflow environments. So once you run your, notebook, this is how it looks like, and you can connect to your notebook. You will get this kind of, screen, and then, you can start coding your effort there actually, right? Coding your effort means you can take a base model from internet, and that base model can be trained, with your own data, or you can do whatever you can do, right? If you have a LLM, you can actually download the LLM, you can fine tune the LLM, but it's all a matter of, writing some piece of code and running it in the Jupyter notebook. And by the end of the notebook run, you would typically save that as an artifact. Okay. But this is good from a, minimal, in the past when you had smaller efforts and scopes actually, right? We are right now at the trajectory intersection of things where we like to adjectivize it this way. The data sets are exploding, the model sizes are exploding, right? So two things are exploding, and this is right. But the point is that from a end user perspective, this is the complexity that they are living in, that every day these data sets and model sizes, they are exploding. And once you start actually, going through this particular process, and you're pretty used to running these notebooks and training your models and all that, once you get into this larger context, okay, and you have to do a distributed training run, because if your task is going to be sequential, it will take ages for you to actually cover the scope of your training, right? And that's what basically means that you will end up in spending sometimes days, sometimes weeks, sometimes months in actually training and optimizing your model. And on a single instance run, this is not a scalable effort, and it basically implies that you could end up in spending a lot of time actually. So what if somebody was to offer you, like what I have, a Kubernetes cluster with multi-node environment? Here I have only 2 nodes with 2 GPU each, means 4 GPUs. What if somebody gave you a 40 GPU farm? How do you utilize that? So in essence, you would start a distributed training run where your one notebook is not enough. So you would create parallel notebooks manually. And then somehow you will have each of these notebook instances, your code, talk to the 40 or 39 remaining notebooks, because it's a cluster now of a distributed training cluster. When I say a cluster, it's not a Kubernetes cluster we are talking about. It's basically, it could be a TensorFlow / PyTorch training cluster, which includes 40 GPU nodes, which means 40 Jupyter notebooks. But then you will have to orchestrate that when they are basically replicas of the same code, but executing part of the code in their own individual realm. And then somehow these 40 notebooks or 40 instances have to converge. They have to talk to each other, so that the state of your training, as it implies, should remain consistent. And then towards the end of it, it is basically an all reduce operation where everything is converged and the output is provided as your trained model, right? So imagine the plight of somebody having to actually build these kind of notebooks and then doing these parallel runs and then orchestrating these notebooks and all that. So in kubeflow environment, you get basically a concept called training operator, which is available for model training. And we will talk more about this and show you also. So training operator, basically, you submit a piece of code to that training operator in the form of a Docker image, where your entire code, that model run, is basically encapsulated into a Docker image, and you submit basically a job to the training operator. And that training operator, like if you were to manually create these 40 Jupyter notebooks, based on your input in terms of number of replicas and the resources that you will provide to that job, like the GPU count and all that, it will orchestrate all that for you. So you don't have to manually do anything. You just have to build one YAML, small one, and say that this is my Docker image. These many number of replicas of this job should run. This is the GPU and CPU or whatever it is actually, right? And parameters that you want to supply. It will execute everything in parallel and return you the output at the end of the run. So this is, I'm progressively building the dialogue, but now there are two things important to understand. And this is where you are getting into the slight, I would say, scavenging the surface or scratching the surface of what is parallelism all about when it comes to distributed training. There are two high-level concepts. One is called as data parallelism. Second is called as model parallelism. Both have their distinct needs as to why would you want to do that. Typically, the first one is to accelerate, because as your data sets are getting larger, you can shard your entire data set into smaller chunks. And let's say when I say that you had 40 replicas of the same training job somehow being orchestrated, but then the input to that job will be your chunks of data. So every job or every instance of that job will execute its operations on a chunk of data, and then convergence will happen, right? Whatever that means. But that is called as data parallelism. Most often it is to actually use a bigger GPU farm and then be able to leverage that speed to actually accelerate your training workflows. Model parallelism, on the other hand, typically you use in the context now in the case of LLMs, where your model, you know that when you are working in GPU context, your entire thing has to come into the GPU memory, including the model associated attribute artifacts, let's say your weights, your everything basically, right? So the model itself represents a size of something, right? And if that is so big that you can't fit it into one GPU's memory. So let's say, your GPU memory is 46 or 48 GB, and given everything else that, is embedded into the GPU memory, some, all the framework requirements and all that, whatever memory is paired, if you are not able to fit your model and model associated things into that GPU memory, then you will run into an error called as CUDA, out of memory error. And that is where this model parallelism typically comes into play, where you can now, instead of sharding the data, you can shard your model itself actually. Okay, which means your piece of code has a certain number of steps to be done. You can actually distribute the chunks in a way of the model that, certain pieces get executed differently and all that. So you split that model itself and draw parallelism into that. Then there are some, sorry, Robert, there was a question, Rob?
Does this mean that there is an equivalent concept of parallel inferencing as well?
Yes, yes. So this is training. Then comes inferencing. So when you run inferencing, you're running an instance of the model, but that model can only be run on like a container typically, right? because most inferencing is now done on top of Kubernetes, right? Either through the Triton server or some K-serve or whatever, Olama and whatnot. But that model has to run on a specific Kubernetes node, which is restricted by the amount of GPUs you have on that node. Now there are concepts like, and we have deployed that. Unfortunately, I don't have the time today, but you see this LWS system, leader worker system, where you have in the inferencing equivalent of splitting that particular model in a way that inferencing also can be distributed over multiple nodes. But that's an advanced topic for a later session or day whenever the time arises. Today, we will focus on the training part of it, actually. So data parallelism and model parallelism. Now, obviously, these are, like theoretical concepts. In reality, when you have to deploy these, you have to take the crutch support of which framework are you using this for, right? So you could have your things being done in PyTorch, or you could be doing things in TensorFlow or something else. Each of these frameworks have specific implementations of how do they achieve data parallelism or model parallelism, or they have blended these both into a superior concept, let's say, right, when it comes to their own implementation frameworks. Okay, so today we will be looking at this something, just a visual. I'll supply this file after the training, but this is just what it is basically. When you are running a TensorFlow training code, and I'll show you the training operator basically will construct these replicas, and based on certain inputs, these replicas will be spun up. And this is, let's say, in the context of data parallel processing or execution. You will need some entity, right, that will help you converge the states of these model runs, actually. And that is called as a parameter server. Again, it is a pod in the Kubernetes. This is called as asynchronous way of doing distributed training. You have a synchronous form of distributed training. And this is only in the case of specifically TensorFlow, where you don't have a parameter server and the workers keep talking to each other. But then there are pros and cons of both. I like this better, where you have some dedicated entity which can continuously receive the weights, receive the, the gradient updates and then pass on the weights and all that, actually, right? And that's how your entire model run exists. But note that this is just one way of doing it. Likewise, you have, in PyTorch, I'm showing it without the parameter server, right? So you don't have any external. The workers, they typically go in a ring algorithm and try to do a execution and then convergence and all that, actually, right? Now, enough theory. I hope this theory part is okay. It gives you just a minute fragment or a peep into the world of what we are going to actually deal with, right? Or what people typically deal with. So like I showed you, kubectl get pods -n GPU operator. GPU operator is running, which means that anything that I deploy can have access to the GPUs.